Alright, in this lesson I'll finish the notes on 3.2 on polynomial functions. So here we're going to talk about x-intercepts and multiplicity. We previously talked about the end behavior of polynomial graphs. Now our focus is going to be on what's going on in the middle. So it says here, find the zeros of f of x equals x squared minus 5x minus 14. Well, first of all, I need to give you the definition of a zero. If f is a polynomial function, then the zeros of f are the values of x for which f of x equals 0. In other words, the x values that I can plug in as inputs, and the output will be 0. So all we need to do to find our zeros is set the function x squared minus 5x minus 14 equal to 0. And this is a quadratic equation, so we're going to try to factor this using the AC method. We need two numbers that multiply to negative 14 and add to negative 5. So 2 and 7 are the numbers that are going to work here. Notice we need opposite signs, so when we multiply we get a negative 14. And the two numbers need to add to negative 5, so I'll need to make the bigger number 7 negative. And so 2 times negative 7 is the negative 14. And 2 plus negative 7 gives you negative 5. Now this is a 1x squared, and so we can use the shortcut here and just plug in these numbers with x. And so we have x plus 2 times x minus 7 equal to 0. The next step is to set each of our factors equal to 0. And when we solve, we get negative 2 and 7. So these are our zeros, negative 2 and 7. F of 7 is 0, and f of negative 2 is 0. So here's our zeros. Now I'm going to go ahead and on the graph, notice I've labeled the x-intercepts, and notice they're at negative 2, 0, and 7, 0. In fact, if I wanted to find the x-intercepts, we know that we need to let y be 0. So if I put a 0 here and solve this equation, that's what we just did, we actually get, remember we're choosing x to be 0, and we get negative 2 and 7, and so those 2 points are our x-intercepts. So there's a relationship between zeros and x-intercepts. In fact, there's 3 things going on here that we can say. First of all, x being a 0, if I work backwards with what we have here, notice we have x minus 7 as a factor. We could go either direction with this. I know if x minus 7 is a factor of this polynomial, that x equals 7 will be a 0. And I know if x equals 7 is a 0, then I can say x minus 7 is a factor. So these things go hand in hand. And in fact, if 7 is a 0, then we know 7, 0 is the x-intercept. Just like if negative 2 is a 0, we know negative 2, 0 is an x-intercept. Alright, so I'm going to go ahead and tie all this together down below here. For a polynomial function f, the following statements are true. C is a 0 of f. So we use C to stand for our 0 here. And let's look at our example to illustrate what we're doing here. So in this case, we could say 7 is a 0 of f. The second thing that I could say is x minus c is a factor of f. If c is a 0 of f, then x minus c is a factor of f. So in our example, x minus 7 is a factor of f. So if I know 7 is a 0 of f, then I know x minus 7 is a factor of f. And it goes in reverse too. If I know x minus 7 is a factor of f, then I know 7 is a 0. And then the last is about the x-intercept. C comma 0 is an x-intercept for the graph of f. So in our problem, it would be 7 comma 0 is an x-intercept for the graph of f. Again, all of these statements are related. If I have one of these, I have the other two. And so that's going to be something that's important as we proceed. Let's move on to the next slide. So it says, consider the graphs to the right. notice the behavior at the intercepts and corresponding zeros. So first of all, what are the zeros here? I'm going to go ahead and darken in these graphs. So I'm looking at this function right here. The zeros are going to be negative. If x plus 3 is a factor, we know negative 3 is a 0. In fact, you can always set the factor equal to 0. And when you solve this, you get x is negative 3, which is the 0. But we know if x plus 3 is a factor, that negative 3 is a 0. If x minus 1 is a factor, then we know 1 is a 0. The corresponding x-intercepts are negative 3, 0, and 1, 0, and you can see those on the graph here. Now there's something more going on here. It says at x equals negative 3, the graph touches the x-axis and turns around. So that's here. And at x equals 1, the graph passes through the x-axis, and so that's there. So I want you to see something here. Notice the exponent on the factor x plus 3, which corresponds to our x-intercept at negative 3, 0. It's even there, it's a 2, and the graph bounces at that point, or at that intercept. The other way that it's going to be sometimes stated, I believe this is how you'll see it in my math lab, is it touches and turns around. I'm just going to use the word bounces. So it hits the line, or it hits the x-axis, and it just bounces back down. It doesn't cross. And then I want you to notice the exponent on x minus 1, which corresponds to the x-intercept 1, 0. And notice that one's an odd power, and we crossed. So let's see if this pattern holds true when we look at the other function we have graphed here. And again, I just want to make the comment that I'm going to use the word crosses, but you may see in my math lab it'll say passes through. All right, so on the bottom function here, notice your zeros are going to be negative 1 and 2, and the corresponding x-intercepts are negative 1, 0, and 2, 0. So let me go ahead and put those on the graph. So notice when our exponent is 3, the corresponding intercept, negative 1, 0, notice it crosses there. Again, that's an odd exponent. And when it's 2, an even number, it bounces. So it looks like we have a pattern here, and in fact this is going to be true. Let's move on and let me make a summary here. The term multiplicity is used to indicate how many times the same factor or 0 occurs for a polynomial. For the function g, let me go ahead and put g down here. X equals negative 1 is a 0 of multiplicity 3. That's because of the exponent there. Since g has 3 factors of x plus 1, in other words, x plus 1 times x plus 1 times x plus 1, that's what the exponent indicates there. For x equals 2, it says x is a 0. X equals 2 is a 0 of multiplicity 2. Notice here you have 2 factors of x minus 2, or an even exponent on x minus 2. So in general, when a polynomial is in factored form, for odd-powered factors, the polynomial will cross the x-axis at the corresponding x-intercept. For even-powered factors, the polynomial will bounce at the x-axis at the corresponding x-intercept. So this is going to help us to do our graph, particularly to understand what's going on in the middle of the polynomial. We've already talked about end behavior. Now we know what's going on in the middle. Or we can use this information to draw the part in the middle. All right, so let me show you how this works. Let's look at number 3. So we have f of x equals x minus 2 quantity squared times x plus 1 times x plus 3. It says describe the behavior of its graph at its x-intercepts. So first of all, our x-intercepts, well, our zeros are going to be at 2, negative 1, and negative 3. And so the corresponding, I'm going to make a little table here. I'm going to label the columns the x-intercept, multiplicity, and behavior, BEH for behavior. So at 2, 0, which corresponds to the 0, 2, or the factor x minus 2, our multiplicity is going to be 2 because of the exponent here. And the behavior, we know if it's even, it's going to cross at that x-intercept. For negative 1, 0, the multiplicity here is 1. This exponent is 1 here. Same thing here. And so the graph will cross at that x-intercept. At negative 3, 0, the multiplicity is also 1, and we're going to cross at that x-intercept. It says, what is the degree of this polynomial? Remember, when a polynomial is in factored form, to find the degree, we add the exponents on the algebraic factors. So that's going to be, in this case, 2 plus 1 plus 1. And so you get 4. Describe the end behavior of f. Well, we know we're even, and notice the number out front is negative 1, and so this is, oh no, I'm sorry, that's a positive 1. And so we're positive, the coefficient out front is positive, and so we know in this situation the end behavior is going to look like this. It's going to rise on each end. And so now we have all the information we need to do the graph here. So we start by putting on our x-intercepts. So we have an x-intercept at 2, negative 1, and 3. And then let's go ahead and put in our end behavior. We know on the ends it's going to look like that. And so now I work from left to right, and when I get to an x-intercept, my little chart tells me what to do. When I get to negative 3, 0, notice at that point we're going to cross. Eventually we have to come back down and go through this next point, or we may not go through. We'll either touch or we'll either bounce or cross. At negative 1, 0, we're supposed to cross, so let's do that. And then notice when we get to 2, the multiplicity there is 2, and so we should bounce, and notice that matches our end behavior, and so we're done. All right, let's move on to the next example, number 4. In fact, I would encourage you to maybe try this, see if you can do it, follow the example that we just did, and then watch the video. All right, so the first thing, notice I didn't give you all the directions here. First thing you want to do is make your little chart. Our zeros here are 4 and negative 2, so our first x-intercept is 4, 0. It's not a bad idea to write out what these zeros are, so 4 and negative 2. And we know wherever we have zeros, we're going to have x-intercepts. So notice the exponent on x minus 4 is 3, so our multiplicity for this, for 4, 0 is 3, and so the behavior we're going to cross because that's odd. And then at negative 2, 0, the exponent there is 1, and so we're also going to cross there. And now let's look at end behavior. The degree, first of all, remember we need to add the exponents of the algebraic factors. So it'll be 3 plus 1 here, and you get 4, so we're even. Notice the number out front is negative 1, so we're negative. And so on your end behavior here, it's going to fall on each end. And so now this is all we need to do the graph. We've got to put in our x-intercepts. Our end behavior is going to look like that. And then when we'll go from left to right. When we get to negative 0, we're going to cross, negative 2, 0, we're going to cross. Eventually we have to come back down to this other x-intercept at 4, 0. And notice there we're also going to cross. And notice that does match our end behavior. Now this is kind of a rough sketch. If you actually graphed it, it looks more like that. Notice it kind of looks like x cubed, or really the reverse, or minus x cubed, or what I call the reverse John Travolta graph. But anyway, what we did up here is a good enough sketch. All right, let's move on to the next slide. I just want to do a quick review. Sometimes symmetry can be helpful to us when we're graphing polynomials. I want to remind you, even function is symmetric with respect or about the y-axis, and an odd function is symmetric with respect to or about the origin. I should have the word "the" in there. And I'm going to go ahead and darken up these graphs. All right, so the first one certainly has y-axis symmetry, and so we're an even function there. Now the second one, be careful, it does have an axis of symmetry. It looks like a parabola, but we don't have y-axis symmetry, and we don't have origin symmetry, so in this case you would say neither. Notice on the third one here, this one's actually got origin symmetry, and so this one is odd. In fact, if you pick a point on one side and you draw a line through the origin, you'll see a point the same distance on the opposite side, and that's always true with origin symmetry. It's basically symmetry through the point 0, 0. And then this last one you can also see has y-axis symmetry, and so it's even. All right, let's move on. This will be our last slide. It says find the zeros, and actually, all the work we've done up to this point is basically so we can do problems like what we're about to do. So it says find the zeros of the polynomial function f of x equals x cubed plus 3x squared minus 16x minus 48. So if I want to find the zeros, I need to factor this. And this is 4 terms, so if you think about our factoring skills, we know when we have 4 terms, factoring by grouping is usually our go-to method. And in fact, that's what we're going to want to do here. So I'm going to go ahead and set this equal to 0. That's how we find our zeros. Set the function equal to 0. We're looking for the x values that cause the function to equal 0. So let's factor this. We can factor out an x squared here. X squared times x gives you x cubed, and x squared times 3 gives you the 3x squared. When we factor these two terms, we're expecting to get an x plus 3 factor, and in fact, negative 16 times x gives you the negative 16x, and negative 16 times 3 gives you the minus 48. So that does work. So that's equal to 0. So we end up with, notice we have 2 terms here, with the common factor of x plus 3, and then if you cross those out, you can see the x squared minus 16. Now x squared minus 16, that's a difference of squares, and so we can go a little further. It'll be x minus 4 times x plus 4, and so we know 3 factors of our function, and so we know 3 zeros, negative 3, 4, and negative 4. All right. On number 8, it says graph the polynomial function. So again, to do that, we're going to want to factor this polynomial. That's how we find our zeros, which will give us our x-intercepts, and then we can do like what we did on the previous page. So first of all, let's go ahead and factor, and we can factor out a GCF of x. And then notice inside the parentheses here, this is a trinomial, it's quadratic. We should be able to factor this using the AC method. So we need 2 numbers that multiply to 4 and add to negative 4. Well, 2 and 2 are the ones that are going to work, and notice they're going to both need to be negative. Negative 2 times negative 2 is 4, and negative 2 plus negative 2 gives you negative 4. So we can use a shortcut here, and we'll just go ahead and plug those numbers in. So finally, we can write f of x as x times x minus 2 quantity squared. So now we're going to treat this just like we did on the previous slide. Now that it's in factored form, we can easily graph this polynomial. First of all, we want to make our little table, and notice our zeros here. You can always set each of your algebraic factors equal to 0 to find your zeros. Notice if x is a factor, then x equals 0 will be a 0. And of course, if x minus 2 is a factor, then 2 is going to be a 0. So we have two x-intercepts and two zeros and two x-intercepts. So let's fill in our table. We need to put in our first intercept 0, 0. Notice the exponent there is 1, so the multiplicity is 1. And so at 0, 0 on the graph, we're going to cross. And then our other one is going to be, our other x-intercept is 2, 0. Multiplicity is 2 here. And so here we're going to bounce. Now the other thing we need to consider is the end behavior. And this one has a degree, well, remember, when it's in standard form like this, we just look at the leading term, and so the degree is 3. And that's positive, and notice out front we're positive. I'm sorry, it's an odd degree, and the number out front is positive, so we're odd, and we're also positive. And so we know that's going to be like y equals x cubed. On the ends are what I call the John Travolta end behavior. So it falls on the left and rises on the right. And so now we can graph this. Let me go ahead and put on the x-intercepts. And we know the end behavior, it's going to look like that. So again, going from left to right, when we get to 0, 0, my little chart tells me I need to cross. Eventually I have to come back down, and notice when we get to 2, 0, we should bounce. And that's exactly what happens. Alright, so that's the end of our video here.